Okay, today we're talking about z-scores and specifically standard error of the mean with regard to z-scores. Now this is a little different than the last lecture where we talked about z-scores with respect to individual scores. This is going to be more about a sample and the relationship between a sample and a population and the difference in the distributions between those two. So what we're going to do, the learning goals for today, is we're going to define central limit theorem and the standard error of the mean, and that's what this SEMp stands for. We'll compute standard error of the mean, and then we'll apply it. We won't compute or apply central limit theorem because it's more of a statistical theory as opposed to an application. So the central limit theorem, the idea of central limit theorem is that as sample sizes increase, so do the bell curve, and so does the normalization of the bell curve. And additionally, increases in sample size also increase the population similarity of the distribution. So what that means is, as we include more people in our sample when we're trying to extrapolate to a population distribution, for example, the more people we include, the more like the population distribution the sample will be. And in addition, as population scores, when we're looking at an entire population, depending on the size of the population, of course, the population will start to become more normally distributed as the population grows. So the more people you include, the more normal your distribution is going to be. So what is a bell curve? And what is a distribution? So the bell curve and the distribution, the bell curve is a visual representation of a distribution. We've talked about distribution before. And so this is your distribution, right? Or a distribution, a sort of theoretical distribution. And this is a normal distribution. And what that means is that, again, this is where on the, and this should actually say x-axis, I apologize. So on the x-axis we have the raw scores or the scale scores, and on the y-axis we have the frequency or number of people. And so a normal, and then this is the bell curve. So the bell curve is a visual approximation of the distribution of scores. And what makes a distribution normal is when you have a lot of people here in the middle, sort of clustered in the middle, and people sort of tail off on either end. So fewer amounts of people have much higher scores than average, and fewer amounts of people have much lower scores than average. That's what makes a bell curve normal, or a distribution normal. And again, the bell curve is just the visual description or visual approximation of the normal distribution, or a distribution. So we'll be using this little line throughout this talk. So let's use an example of central limit theorem. So this is a normal curve, right? This is our normal bell curve. And let's say this is the population. And so what central limit theorem says is that you may be able to take a sample of that population, but the sample may or may not completely add up to the population. So this might be your sample right here, right? And as you can see, it might have the same distribution, but it's not the same as the population. The distribution itself isn't the same as the population. We've taken a sample that's a little on the tail end side of this. But the more samples we take, the more the population distribution is going to, the more the sample is going to look like the population distribution. And so that's the point of central limit theorem, is that the more people you take in a sample, the more likely it's going to look like that distribution, and the more likely that distribution is going to become normalized. And this also goes the same when you have a population with a skewed distribution or a non-normal distribution. So we can take a sample of a population with a skewed distribution, and the more samples we take, meaning the more people we include in a sample, the more likely it's going to look like that distribution. the distribution of the population, that is. And so what does this all mean? And the point of this is that sampling is a big part of statistics, and it's a big part of doing research. And I'm sure you can understand that it's oftentimes impossible to take data from the entire population, to understand the entire population in its whole. So what we do is, as social scientists, is we take samples to estimate what the population is. And as part of that estimation, and the estimation means it's not exactly correct, we have some error in our sample with regard to with regard to the population. So there's a difference between the sample and the population. And so we use the sample as an estimate of the population. So the more people we can include in a sample, the more like the population it's going to be. And so this is where the standard error of the mean is. The standard error of the mean is a calculation that describes this, right? So it describes the difference between the population's distribution and the sample's distribution. And we can create an estimate based on that. And so the calculation for the standard error of the mean is the standard deviation of the population divided by the square root of the sample frequency, or the sample population, or the sample size, right? And so this is the calculation for the standard error of the mean, and we'll put this in application in a minute. And so, as I said, the sigma here, our little sigma, is the population standard deviation divided by the square root of the sample size, meaning the number of people in the sample. And so this calculation gives us the typical error that we're going to have with regard to our sample versus our population distribution. And again, the greater the sample size, the less the standard. So let's take an example, and this is, the question is, what is this good for? Like, what does this mean?
What do we want to know with this? So let's use this an example for schools. So I'll just read this little paragraph, and you can read along with me. Let's say students in 5 schools in Washington were found to have potentially inflated SAT scores. As such, these schools were sanctioned and program funding was pulled. And so what we have here is the state or population mean on the SAT is 1100, and the standard deviation is 200. So it's a fairly standard deviation. However, among these 5 schools, the mean for the 25 students in total who had taken the SAT across these 5 schools was 1200. So the question is, what is the probability of obtaining such high scores just simply due to chance or sampling error? Right? Was this sample of 25 students significantly, were their scores much more inflated compared to chance? And so this is what the standard error of the mean tells us. And when we put this on a z-scale, this is what we can come up with, and these are the types of questions we can attempt to answer. And so let's put this in practice. So we're calculating the SEM, the standard error of the mean. So what we want to do first is compute the observed deviation scores. And so the observed deviation score here is the mean of the schools, or the mean of the students on the SAT, minus the standard mean, or the population mean. And that gives us a 100, right? 1200 minus 1100 is 100. Step 2 is we have to compute the SEM, the standard error of the mean. And we do that by taking the deviation score, right? Remember the equation before. So we take the standard deviation and divide that by the square root of the sample size. And in this case, the standard deviation for the population was 200 divided by the square root of the sample size. The sample size in this case was at the student level, so it's the number of students in the sample, which is 25. And what we get here is 40. That's what this equation adds up to. Step 3, we compute the sample z-score. So we essentially do the same thing, just like we calculated a z-score for individuals. We're going to do the exact same thing, but this is a z-score on the this is slightly different because this is a z-score for a for a sample, not a population. So it's a z-score for a sample and not individuals. But you can sort of think of it as an individual sample, if that helps. So we calculate the sample z-score. So it's these two equations put together. So the mean minus, or the sample mean minus the population mean divided by the standard error of the mean. And so what we have here is 100 divided by 40, which gives us 2.5. Now what we can do is we can look up this score. We can look up 2.5 on our z-score table. So you remember your z-score table in Appendix A. So we look that up, and what we find is the sample z-score is at the 99. What that means is these 25 students among these 5 schools scored
99% higher than everybody else in Washington. So their scores taken by chance are fairly inflated. So if you take the flip side of this Washington scored higher than them. So this sort of indicates that these scores are potentially artificially inflated. Because they're so high. So they're either potentially artificially inflated, meaning they potentially cheated, or they're just extremely smart kids, and schools are preparing them very well for the SAT. And so that's sort of what these scores are differentiating here. And so to bring it back to the learning goals for this lecture, what you want to know is the central limit theorem. So distributions will generally fall into a normal curve, and the larger the sample, the closer to the population distribution. And then for the SEM, for the standard error of the mean, that is the difference between a population's distribution and a sample's distribution. We also calculated the standard error of the mean, and then we applied it. And what it tells us is it tells us whether a sample distribution is untypically different from the population's distribution. So if we have a sample distribution that is not very typical of the population distribution, then that's telling us we don't have a good sample, or there's something going on with that sample, and we need to either add to it or take a different sample.